Okay, in this little setup for our experiment today, we're going to be discussing the rates of dissolving, well, basically how fast things dissolve. And there are three variables which we can mess with to change the rate of dissolving. The first is temperature, and over here we have hot water and we have cold water. The second variable is whether or not you agitate. So here we have water that will be agitated. Here we have water that will not be agitated. And the third is surface area. So here we have a sugar cube that is compacted all together. So the only exposed surface area are the outer edges. That exact same size sugar cube over here has been crushed up. So we expose a lot more surface area for this sample over here. Okay. We want to keep our variables the same and only change one variable at a time. So for all the experiments, we're using 150 milliliters of solvent, and our solvent is water for all of them. In all experiments, we're using a single sugar cube. For the most part, is the same mass for each one of our sugar cubes. Okay. We're going to run through each one and do a comparison between hot and cold, agitate or not, high surface area or low surface area for our different things, and then talk about which one allows things to dissolve faster. Okay. So the first one we're going to put in is our sugar cubes in our hot and our cold water. And we'll drop those two guys in like that. And we'll take a look and see what's happening. So here's our hot water. Here is our cold water. And at first we don't see a lot going on. But we notice that the sugar cube for the hot tends to be breaking down much quicker inside of here. And the sugar cube for the cold, not nearly as fast. We'll come over to our agitation versus not, and we'll drop a sugar cube into each one of these. And again, we have a stir stick in this one that is agitating the solution here, and here we are not agitating it. These are both at the exact same temperature water, so here the only variable we're changing is whether or not we are agitating. And again, upon first glance, we see that that sugar cube that was agitated in that solution seems to be dissolving much faster than the one that is not being agitated. Finally, we'll come over here to our solutions that have high surface area versus not high surface area. So first, the high surface area, we're going to dump that in and then drop that one in very quickly behind it. And same mass, but because we crushed it up into smaller pieces, we have more surface area. So get that in and get the other one in so they're relatively the same time, and we'll take a look and see. And now if we come over here, we take a look, and with the surface area between the two, we see the one with less surface area that was originally a cube slowly breaking down and actually exposing more surface area. Whereas this one that had the surface area exposed sooner is dissolving faster. It's not quite as obvious here because we're not agitating this, but if we were to agitate both of these, that result would have been more obvious. It's also not quite as obvious because the sugar cube here was actually allowed to break down to expose more of its surface area in the solution. But even so, we can see there's a thicker pile there and the remnants of that first cube, where here most of that has dissipated at this point. Okay, so from that we can now conclude that if you are hotter, you dissolve faster, if you agitate, you dissolve faster, and if you have more surface area, you dissolve faster. So the question becomes why for each of these scenarios.
The next kind of topic we want to roll into is how fast something dissolves. So there are three things that affect the speed of dissolving. We're not talking about how much yet. We're talking about how fast we can get something to dissolve. Those three topics are surface area, agitation, and temperature. Okay? Now, all three of these factors come down to one thing. They're all based on how do you get more collisions to happen between the water molecule and the salt, or the water molecule and the polar molecule. Okay? So we want to increase collisions to increase the speed of dissolving. So for surface area, if you crush it up and make as much surface area as possible, you now have more spots for collision to happen. More spots means more collisions, means faster dissolving. Agitation, if you physically just stir it, what happens there is you're actually moving water molecules that would normally be further away from the crystals closer to them, and you're actually moving the water molecules that have already dissolved crystal away, and you're keeping an even concentration always. So by physically stirring, you're actually providing a better system for more collisions to happen. So again, you get more collisions. Now, temperature is all about kinetic energy. So if we raise the temperature, the particles will be moving faster. If they're moving faster, well, the faster they are, the more collisions that they can have happen. Also, the faster they move, the more energy they have. So more of the collisions will have enough energy to start splitting apart the crystals within those crystal lattice. So all three, a little bit different ways, but all three generate more collisions if you increase them. So if you increase surface area, increase agitation, or increase temperature. Now, if you wanted to slow this down, you would do the opposite. So you'd want to have the least amount of surface area. You would not want to stir it, and you want to make it as cold as possible in terms of slowing the process down.